And so if you are struggling on multiplying these polynomials, you might want to switch to the area model. Now, I am going to collect this and we're going to go over it. So we got a lot of wings. Yeah, by the way, you know it says who is to your left and what is their favorite food? Most of you, I only have one person actually respond to who is to their left. It doesn't help me know what the food is unless I know who the person is. So Caroline likes wings. Several other of us like wings, pasta, tacos. Alright. So, here's what we're looking at now. Multiply -2. Nope, that's not what I want to do. -2 times x plus 3 squared times x minus 1 to get the standard form of the function. So, first things first. Some of us need to pick up a pencil along with a sheet of paper and take some freaking notes. Some of the rest of us need to get our notes out when we are doing this since we are struggling so hard with this. I am so tired of you being lazy and as a result of laziness not knowing how to do this. All you have to do is get out your textbook and look somewhere in the textbook or get out the graphic organizer where you should have examples of this. We gotta know how to multiply polynomials. I'm telling you right here and right now, you got 2 problems of multiplying polynomials on your understanding check on Friday. You don't know how to do it, and today's the last day we're going over it, you're missing out on those points. Now, a couple of students asked a key question. They said, hey, Mr. Kinney, can I leave the -2 until the end? 1, yes you can. 2, that's what I would recommend. Do not worry about that coefficient, that constant out in front, until the very end of the multiplying process. You might want to get a sheet of paper to write notes. Legitimately, y'all, there's a connection between writing and memory. The more you write it out, the better you'll remember it. That is not a lie. There is psychological tests or studies done on that. So, a lot of us did very successfully, I will note, realize that this is x plus 3 times x plus 3. It's right there. The next detail we need to remember about multiplying polynomials is how many polynomials can you multiply at a time? So, just 2. But you need to multiply the polynomials to start. And what are the 2 methods that you can use in order to multiply polynomials? You get the area model, right? Or distribute. I'm going to look at this x plus 3 times this x plus 3 first, using both methods so you can see how they are the same. So I'm only going to do the x plus 3 times the x plus 3. When I distribute, what do I do with this x? What does it mean to distribute though? I am multiplying. I am taking this x and I am multiplying it by that x and by that 3. So x times x is x times 3. That is distributing that first x. I still need to distribute this 3. So how am I going to do that?
3x plus 9.
So plus 3x plus 9. Now, I saw some students wanting to then write x squared plus 6x squared. Hello? Yes, ma'am. Okay. Sounds good. Yes, ma'am. All right. So, what is wrong with this right here?
Because you don't do that. You only add the exponents when you multiply.
Remember, you only add exponents when you are multiplying powers with the same base. Remember, what does it mean to have x squared? What does x squared really mean?
X times x.
X times x. Am I multiplying x's right here at all?
No.
No. I have 3 x's that I'm adding, and I have 3 more x's that I'm adding, so I have 6. Alright. What I want you to see though is, that is identical to using the area model. All the area model does is helps you organize that multiplication. X plus 3 times x plus 3. What is x times x? X squared. Same as this x squared. What is x times 3? And then 3 times x. And 3 times 3. And you can even see those like terms right here. 3x plus 3x is what?
C6.
Same exact things, right? Please understand, the area model is not a different way to multiply the polynomials. It's just helping you organize that multiplication. It is just helping you organize the distribution. That's it. But what you have to recognize is, what I've done is I've only multiplied x plus 3 times x plus 3. That's x squared plus 6x plus 9. What do I still need to multiply that by? Times x minus 1. Again, I'm going to leave that negative 2 to the very end. And you can distribute, you can use the area model. Personally, I'm going to distribute when it's binomials. When it gets to a trinomial, I might move to the area model. But again, does it matter which one you use? No. You use whatever works best for you. X squared plus 6x plus 9 and x minus 1. I'll even point out, it doesn't matter which way you orient the area model. X minus 1 and x squared plus 6x plus 9. It does not matter how you set it up. You just need one polynomial along one side with a number of boxes equal to the number of terms, and then the other polynomial on the other side. You can do some trinomials, you can do it with 4 terms, 5 terms, however many you have. So Maven, what is x squared times x? X cubed. Mia, what's x squared times negative 1? Say again. Negative x squared. Anaya, what's 6x times x? 6x squared. Braden, what is 6x times negative 1?
Negative 6x.
Caroline, what's 9 times x? 9x. And Devin, what is 9 times negative 1?
No.
Okay. Do we need to edit any of these, or do we think they are all correct?
Negative 9.
Negative 9? Why do you think it's negative 9?
I think you multiply by a negative.
Okay, so Devin, what do you think about that? 9 times negative 1 is supposed to be negative 9. Yeah? Okay. So be careful about those signs, but also remember, if you make a mistake on multiplying, you can still do okay as long as you show me what you're doing and I understand it. Key, am I completely done now? Okay? So how do we write this?
Yeah, I found I time.
Okay, and so I will say, I was trying to get Key to get there, but Ralston's correct that in order to, now first off I will say, do I need an equation in this case? Why not?
Oh, you gotta add it too though, for real.
That's not what I'm asking.
Because it's not supposed to equal.
Oh, no, man, like,
In order for it to be an equation, it needs to what, Anaya?
oh,
Equal something.
it's just,
So what do we call this?
state? No.
I was about to say that if inequality,
Is there an inequality here?
no.
No. What is
In my head.
a mathematical,
Solution?
not a solution, what is a solution? Come on now.
Oh, that's the answer.
That's not the answer.
Oh,
Say it again. It's an expression is what we're looking at, right? There's no equal sign, there's no inequality sign, it's just an expression that we're looking at. Come on, we need to know what a solution is though. What's the solution?
solution. That way back in the day.
That's solving, but a solution does something to equations and inequalities. Thank you.
Yeah.
A solution only makes the equation true. So, any like terms for this negative x squared?
Oh, yeah.
6 minus 1x. Well, 6 minus 1.
So,
Five.
Yeah,
6x squared.
5x squared.
Any like terms for the negative 6x?
9x minus 6x.
Okay. So x cubed plus 5x squared plus 3x minus 9. Am I done?
No, you need
like
two now.
you would add a 2.
I need to add
You
2.
gotta multiply.
Add the 2, multiply it to the,
You can leave it like that, can't you?
expression.
Or you want
You need to finish it. Now, does anyone know why I keep emphasizing this word add? We need to be careful with our language.
Because you're not adding it, you're multiplying it.
Right. When we say add in just English, we usually means to put something else with it, right? Which we are kind of putting something else with it, but don't forget, we're not adding mathematically, we're multiplying. So now we just need to distribute here.
Negative 2x cubed.
There is our final expression.
You gotta quit, man.
Any questions about this? Okay.
Move on to the second, third.
So summarize what we learned yesterday. Let's see what some of y'all responded with. All 5 of us, huh? Yikes. Exponential growth, exponential decay, growth and decay, minimum range, how to match graphs with a table, we did learn about that. So exponential growth, the base is greater than 1, then the function is growing. So notice we need a little bit more detail. So if an exponential growth was when the base is greater than 1, what was an exponential decay?
When?
Okay, so when the base was greater than
0.
0 but less than
1.
1. Remember how we said it was between 0 and 1, right? So if I have y equals 3 raised to the x, is that going to grow or decay? Anaya says grow. Kanye, what do you think? Grow as well?
The decay is greater than 1. What?
I know Kanye said grow too. Why do you think it's growth?
It's grow because it's greater than 1.
Right. Notice it literally says right here, growth, the base is greater than 1. You just said the base is greater than 1, so it's going to what?
Grow.
It's going to grow. What's another mathematical term to indicate that it is growing? That's a term we introduced in polynomials. Increasing, right? So that function is going to be increasing. What about y equals 0.9 raised to the x? That's going to decay? Or another mathematical term for that is?
Decrease.
Decreasing. Okay, so what about y equals 13 divided by 11 raised to the x? Last one.
Draw. You gotta put in the calculator.
You don't need to put it in the calculator.
Increase.
Why do you think it's increasing?
Values.
How do you know the value is greater than 1?
True. It's gonna be 1 and 2 now.
What would the numerator need to be in order for this to be 1?
13. I mean,
The numerator would need to be 11.
Yeah.
See how the numerator is greater than 11?
It's 1 and
So that's greater than 1. Those are things we want to pay attention to. Also, what kind of bases could we not have for an exponential function?
So you said 0.
We could not have 0. What else?
1.
1.
And
What else?
negatives.
And negatives. Remember, that negative is when it started alternating. We don't want that. Alright. So playing from the current slide. So we almost finished up yesterday with just the exponential growth and decay. That beginning of the lesson, we are here on activity 2.1. This is page M3-110. Let's go ahead and get those textbooks out. Come on, Caroline, Mia, come on. It's been all of 5 minutes. Y'all can't be asleep like this already. Mia, you're doing so good. I turn out the lights and you immediately put that head down. Come on.
Yeah.
Yeah, this is
I forgot one.
yeah, volume 2 ain't missing.
Y'all.
It's not him. I'm not going to my car.
Yeah, like you want to college.
It should be volume 2.
What page?
M3-110.
Almost there.
Y'all, what textbook do we need to bring with us every single day from now on? Volume 2. I need you bringing your own volume 2 so you can take notes in your textbook. Who else needs volume 2? Caroline, do you need volume 2? Okay, then please get it out. It's already out? Okay. Everybody over there good? Alright. M3-110. Okay. So, let's look at this together. Number 3, write an exponential function that satisfies the given characteristics. We already talked about some key details with A, B, and C yesterday. What did we say about A?
Exponential growth.
Why do we say it's exponential growth?
Because B was greater than 1.
I mean, we wrote that B is greater than 1, but do we have that information given here? So Mia, how did we know this was exponential growth yesterday? The symbols you guessed. Pick up that head. There's more. What symbols are you referring to? Whatever what is. Well, you're talking about right here, right? Anyone know what that's called? That's, I mean, there's infinities there, yes. So that would be a domain interval, right? That's an interval notation. But we said exponential growth here, but here when there's that same exact notation, we said exponential decay.
Because one says increase and one says decrease.
There we go. This is a detail that we've been talking about, that we have exponential growth and exponential decay. So it's increasing here, and it's decreasing here. But I want you to notice, Caleb, we wrote a detail down that you wrote down, but was that detail ever given to us about the base being greater than 1? So can you say, hey, it's exponential growth because the base is greater than 1? No, because that's not evidence you have. The evidence we had is increasing, so it's exponential growth and b is greater than 1. That's what we need to recognize here. You have to start to think more logically of what evidence am I given and how can I use that evidence. You weren't given the b is greater than 1. We figured that out because we knew it was increasing. So if this is decreasing, we knew it was exponential decay, and what do we know about the base? So remember, it has to be between 0 and 1. Did we ever actually say what C was yet?
No.
Okay, I want you to take, let's say 60 seconds, talk about it with your group, pay attention to the information given, and I want you all to figure out as a group what kind of, whether it be growth or decay. Hey Tris, do you want to jump up with this group here? I know you and I usually talk well. No? JK and I, she don't want to talk to you. There's 0 talking right now. 60 seconds has already started. Let's go.
Caroline, get your head up before I
I'm
get
saying.
upset. I'm highly upset. I'm already ready to hit with you. You keep putting your head down. Keep failing us as a group. You can't learn it. Last time, tell you, today. Biscuit, now you need to talk.
It's okay, Tristan.
Now get up, you gotta teach me about yesterday, 'cause I went
Mr. Kelly,
What?
we just
I thought you said you was gonna explain this.
I want you to think about it at least for 60 seconds. You have no idea whether it's growth or decay?
These two. Was 0 Look like growth.
Okay.
You got it and infinity. Well, infinity is greater than 1.
Okay.
I think,
Alright.
it's exponential.
Okay. So let me say this. Raise your hand if you believe that it is exponential growth. Got a few people. Raise your hand if you think it's exponential decay. Raise your hand if you didn't put in the time to think about it. Some of us are just still confused.
Raise your hand, kid.
Alright. So, Ralston, what were you saying? Why were you thinking it's exponential growth? You were starting to get there? Or you were starting to say some ideas?
Let me see why I think. Probably probably just the points. I don't see no negative points. That's why I get that one. I want to hear your space one.
Okay. Some thoughts? Anaya? You were thinking growth. Why?
Maybe because negative infinity is less than 0 at
Right.
the same time.
Yes.
And then you end with infinity on the next one.
Okay.
Yeah.
Brayden, what were you thinking?
Let's say growth.
Okay, why?
I don't know.
Oh my gosh, y'all are killing me.
Yeah, I can't.
See, here's the thing. Y'all are just blindly staring at these symbols, but did anyone take a second to just think about the general shape of an exponential growth? What does an exponential growth look like?
A U.
No, ma'am.
Hello.
That's a parabola for a quadratic.
And
That's the bottom goes up.
Starts, so on the, you're talking about from left to right, so it starts down here?
Yeah.
No,
it starts
It started in the
like,
first quadrant.
yeah.
Like,
If it's
Did it?
exponential, why would it start in the first one?
You said
Now,
growth.
why don't you go look at the graphs we did yesterday? Look at all the ones that were exponential growths.
start in the second.
So it started in the second quadrant.
And then it
And
goes.
then it
Near
goes
what, by the way?
Zero.
Zero.
No,
Yes, 0 in the
It
what?
starts with
No, 0 in the, which variable?
Oh, it.
Well, 0 in the x is right
Why?
here.
Why?
So it started at 0 in the y, or close to it, meaning it started close to which axis?
The X.
Okay, so it started close to the x-axis, and then it shot up like this?
Yes.
Okay. And I want y'all to hear me very clearly on this. How many of us blindly stared at this and just didn't think to go back and look at our notes or our work from yesterday? You don't have to raise your hand, but I need y'all to think about this. Everything in math builds, and I need to do a better job of telling students this, but that means that you need to look at what we have done in the past to make sense out of this problem. So this would be an exponential growth. What did a decay look like?
It starts
It's
in the
backwards.
first. Yeah.
Starts backwards, so what do you mean?
It starts in the,
Right
yeah, the first quadrant.
It started number 2.
In the first.
Okay, let's be careful about this. How do we always read a graph?
Left, right.
Left to right. So it's not starting in the first. You always start on the left-hand side. But tell me about the left-hand side of the exponential decay. Starts at the top, so like with an arrow up here,
Yeah. No. Yeah.
and then it comes
now.
It go in the first.
Yeah.
Oh, yeah, yeah.
like that.
Yeah.
Not
Well,
like
they
that,
supposed
but
to go
yeah.
straight
Hey, let me
to
ask you a
the
question. What's the end behavior of this? What would the left-hand end behavior be?
Negative infinity to 0.
That's not end behavior.
Positive infinity.
No, it's not.
Infinity.
As x approaches what?
Oh.
Yeah, it approaches
Infinity.
positive.
Y'all, I said left hand.
Oh,
Where's left?
at left.
Negative
Negative
infinity to positive.
As x goes, hold on, you're doing interval notation.
Well, I give up.
No, don't give up. There's literally an example on this page of what end behavior is written like.
Negative infinity, and then the y.
Oh.
And
Yeah.
y
Arrow.
approaches negative infinity. Y approaches-
Y'all, you understand that end behavior is on your understanding check on Friday, right? 2 days from today. We've been doing end behavior for about 3 weeks now. It should be in our notes. Except most of us just wrote for our definitions. Robert, can you get off the calculator, pick up a pencil, pay attention, and take some notes? Thank you. Most of us on our end behavior just wrote as x is going to the left or right or something, some simple definition, instead of actually making examples to go off of or writing out exactly how we're supposed to write these things. You need to put more time into your graphic organizers so that you have something to study. That's the point. Maybe don't close those eyes, you're going to fall asleep. So as x goes to the left, as x goes to negative infinity, what's happening?
Y approaches positive infinity.
Thank you. Y approaches positive infinity. For the right-hand end behavior here, does it?
No.
Look at that again.
0.
Thank you.
Flat.
It's going to flatten out, and it's not going to get to 0, but it's going to approach what?
0.
0.
Smart.
Hey, does that end behavior match this end behavior?
Yeah. No.
You're just saying stuff.
Yeah, I do.
I can't see for him.
You said it's backwards?
Yeah.
Look in the book.
They put the right hand one first.
Did they put the right hand one first?
Yeah.
Yeah, they did.
Are you sure about that?
No.
Couldn't that still be left-hand behavior,
Oh,
but
wait,
it's
no,
still the
no,
way
no,
around?
no, no.
Say again.
Couldn't that still just be left-hand behavior, but it's the other way
That's
around?
still left hand in behavior.
Yeah.
But it's not the same in behavior. How do I know that it's left hand and not right hand?
Because me and the man.
Cause you,
And it's coming from the smallest.
Negative.
It's going from the
I
smallest.
bet say, don't you leave it a graph left to
He
right?
said negative.
Y'all,
Okay.
x is going to what?
Negative.
Negative infinity. Which direction is negative infinity in the x?
No.
Well, then what you suggested.
That's what I said!
But you're 1 out of 3, 8, 12 people.
Then I
Because that
said
was
it's
right.
because it's the smallest on the left.
But you can't say that. Like, it's not, because there's x and there's y. You can't just say it's the smallest. I need y'all to
On
pay.
this side is not gonna be small.
But there's also the y direction too.
About X, Miss Kim.
We are, but you need to then say that.
Yeah.
Okay, I need y'all to pay attention. The left hand in behavior tells me x goes to negative infinity in this case. We have to think about the left hand side of the graph. You can't just say, oh, there's the 0, so that's right hand. No. Right? For the right hand in behavior, y went towards 0 in a decay. So is this function a decay?
Yeah.
Yeah. No.
No.
Y'all just said
No.
stuff before you even thought that time.
No.
You said.
No, I said,
It's a
is
growth,
it?
though.
No, it's
No.
growth.
Okay, why is it growth?
We can never sit down.
Cause the right hand, because your right hand is positive, so it's growth.
Thank you, the right hand
Just
is going towards infinity. I misheard what you said then, that's my bad. But y'all, my whole point was that this is decay.
Yep.
That in behavior for decay did not match this in behavior, so is it decay?
No.
No, it has to be
growth.
growth. Literally what we're saying is, as x goes to the right towards positive infinity, y is going up. Which is what I heard Braden kind of saying earlier, even though he didn't want to say it when I asked him earlier, in the whole class. Does that sound familiar?
Yup.
Stop being scared.
Okay.
You say that every time. Okay, Mr. Kennedy.
Cause he don't say nothing else but then an eye and smile. And he said,
Look. So, what I want us to know then is this has to be exponential growth. And so we know that b is greater than 1. Is that all that they're asking us to do in these problems?
No.
No.
Yeah. Oh.
No. What does the actual direction say? Right what?
Exponential function that satisfies the given characteristics.
So, we need a function. F of x equals what? Any guesses?
0.
It's a growth, so yeah. Wait, no, you can do 3.
Okay? So notice it has to be a growth, right? So b has to be greater than 1. So maybe 3 raised to the x?
Sure.
That's what Anaya guessed. I will say this, that can't work because of the other detail.
Wait, so can you do?
What do I mean by it can't work due to the other detail?
Well, if they got an increase, so it's kind of doing that, but you gotta look at the reference point too.
But we also have to,
The exponent is 0.
Well, we do have that, 3 raised to the x. But I'm talking about the other detail here, the reference point.
So could you use the 6? The y?
Y'all think? Okay, we have this reference point, right?
Mm-hmm.
So when x is 1, what is y?
6.
So if I put a 1 in here for x, do I get 6?
No.
No.
It should be. Never mind. 2, 1, 3.
So we think 2 to the x?
No.
No,
Hold on, wait, wait.
2.
3 to 6.
Yo, let me ask you this, what's 2 to the first?
2.
2. What's 3 to the first?
3.
3.
3 to the second. No. Never mind.
Okay, so what we do is we have to keep the x.
We have to have an x of 1,
Oh.
and we have to have a y of 6.
6.
6 to the x?
Yes.
Is that increasing?
Yeah.
Does it have that reference point of 1 comma 6?
Yes.
Okay, now we got an equation.
We spoke.
We're just not fully thinking through everything, but it's okay.
Alright, so.
So let's think about B.
Well, you can't use either one of them right there. From
What
the
do you mean?
reference point.
Huh?
Because 4 is greater than 1. Oh, wait, yeah.
Careful there.
And then you can't use negative 1.
Well, but
Because
what
that's
is,
less than 0.
but what is negative 1?
4x.
Negative 1 is the x.
Negative 1 is the x. So,
Never mind. More than one.
hold on, that's not the worst idea. 4 raised to the x, right? We used the 6 earlier, didn't we?
Yeah.
Okay, but what's the problem here?
Negative, but it has to be between 0 and 1.
Okay, we know the base has to be between 0 and 1, don't we?
Mm-hmm.
Yeah.
Okay. Also, I want you to think about this. If I were to substitute negative 1 in for x, pick up a calculator, what is 4 to the negative 1?
I don't know why I was supposed to say
And they
that.
can do it because they can scream out.
1/4?
Yeah, 1/4.
That's the reciprocal of what I want.
What did you say?
4-1.
Huh?
What the
Oh,
decimal
one.
point?
4, 1?
No. No, not true.
Like put 4 divided by 1 here?
0.25.
Put a
That's
0.
what I got when I made a decimal.
Okay, but what we need to figure out is what base do we need here? We need something between 0 and 1.
0.25.
Put 0.25 here?
Sure. If you were to do 1/4, you'd do 0.25.
Sure.
I mean, let's check. 0.25 raised to the x. Let's see if that works. Substitute a negative 1 in. Yeah, it helps you even if they shout it out first. It helps you to put done in the types in the calculator. 0.25 to the negative 1 gave me 4. Huh.
Yeah.
Huh. What is 0.25 as a fraction?
1/4.
1/4? Hey, by the way, do y'all know how you can use a calculator to give you the fraction from a decimal?
Yeah.
No.
You said it
Yeah.
yesterday.
Everybody pick up a calculator so that you learn how to do this skill because this is important, or useful at least. Type in 0.25. After you type in the 0.25, hit math,
Math.
or sorry, menu, not math.
Oh.
I'm not thinking. Anybody see an option that would allow us to work with numbers?
Number.
Oh, number. Go to number.
And then click 2.
And then click 2. You mean approximate to a fraction?
Yeah.
1/4.
1/4. Oh, that's useful.
Yes, sir. Read.
All right. So 1/4 to the x. So f of x equals 1/4 to the x. Notice that 4 still mattered, and that'd be useful to notice.
I ain't even trying to figure C out.
We can. We're just. I want to focus on other mathematical things. So, here's what I want us to look at. This table is a summary of everything you need to know from this lesson. This is also a summary of some of the most important ideas that I will be checking for on understanding checks, and you will need to consider when it comes to the next part of the unit that we study. Within your small groups, I want you to take about 5 minutes, and I want you to think about the domain, the range,